Unit 6, sections 1 and 2, which looks at discrete probability distributions. Discrete probability distribution or probability distributions for discrete variables. It lists all the possible events and their associated probabilities. And one thing to note is that the sum of all the probabilities must add up to 1. Now I'll use an example to explain what this is saying. Now let us consider a die. Okay, the die has 6 sides with numbers 1, 2, 3, 4, 5, and 6. Now notice this variable is discrete. We're going to define our variable x as the value shown on the die. So we're going to toss the die, and our random variable is the value shown on the die, which is discrete. Now the table below shows all the possible values of x, 1, 2, 3, 4, 5, and 6, and the probabilities associated with each of these, right? So that's what I was saying on the slide before. Lists all the possible events or outcomes and their probabilities. Now the other point is that the sum of the probabilities must add up to 1. And if we look back at this example, 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 adds up to 1. Let's look on the second example. Let's consider a family of 3 children. Now, let the random variable be the number of girls. Now, this is a discrete random variable, the number of girls in this family of 3 children. Now, x is the number of girls. Now, the possible values of x could be 0, meaning there are no girls, 1, meaning there's 1 girl, which would indicate that there are 2 boys. X could be 2 girls and 1 boy, and x could be 3, all 3 children were girls. Now, the slide indicates the possible ways in which we can have this. For us to have 2 girls, it could be the first one was a girl, second one was a girl, last child was a boy, or it could be girl, boy, girl, or it could be boy, girl, girl. Similarly, if x is equal to 1, that is 1 girl, it could be boy, then a girl, or boy, then a girl, then a boy, or girl followed by 2 boys. Okay, so note here that there are 8 possible ways in which the family can have 3 children. 8 possible ways in which that can happen. Now we're going to put that on a probability distribution table. So x is the number of girls. So notice all the possible values of x are indicated here on the table, 0, 1, 2, and 3. And the probability associated with each is also written on the table. Now, if you recall, there was only one way in which you can have no girls. So that's 1 out of 8. There were 3 ways in which you can have 1 girl. So 3 out of 8, etc. Again, the sum of the probabilities add up to 1. 1/8 plus 3/8 plus 3/8 plus 1/8 is equal to 1. And note also that each of these probabilities is greater than 0. The probability must lie between 0 and 1, which we looked on when we started Unit 5. Now let's use that same table to determine what's the probability that x is equal to 4. Now recall that we define x as the number of girls. So what's the probability in a family of 3 children? So what's the probability that x is equal to 4? What's the probability that x is greater than 2? That is, the number of girls is greater than 2. And what's the probability that x is less than or equal to 1.5? That is, the number of girls is less than or equal to 1.5. Now, the probability that x is equal to 4 is equal to 0. Right? There's no chance that there'll be 4 girls in a family of 3 children. Okay? So that probability is equal to 0. And also, the table shows all the possible values of x. X cannot be equal to 4. X can be equal to 0, x can be equal to 1, x can be equal to 2, x can be equal to 3. Anything outside of that would have a probability of 0. Now the probability that x is greater than 2. Now what are the values of x here that are greater than 2? The only value is 3. So we're asked to find the probability that x is greater is equal to 3. And that corresponds to 1 over 8. The probability that x is less than or equal to 1.5. What are the values of x that are less than or equal to 1.5 on our table? And that would be 1 and 0. Those are the two values of x that are less than or equal to 1.5. The probability that x is equal to 1 is 3 over 8. Probability that x is equal to 0 is 1 over 8. That adds up to be 4 over 8, which is equal to a half. We're going to move on now to cumulative probability distribution, which is denoted by a capital F of x. Now, cumulative, we looked on cumulative frequency in Unit 3, and Unit 3. And so you have an idea of what it means by cumulative frequency. Now, this is cumulative probability distribution. Now, the concept is the same, where you're going to be adding the frequencies as you go along. So the cumulative probability distribution, notice here my formula, f of x is equal to the probability that x is less than or equal to some value. Okay, so I've inserted a third row here to indicate the cumulative values. The first value will be 1 over 8. Now the next one will be 4 over 8, because that's 1 over 8 plus 3 over 8 gives me 4 over 8. Now I'm going to add 3 over 8 to give me 7 over 8. Then I'm going to add 1 over 8 to give me 1. Okay, of course, the sum of the probabilities must be equal to 1. So this final value must always be equal to 1. So if we're asked to find the probability of f of 1.5, that means we need to find the probability that x is less than or equal to 1.5, which we found on the slide before to be a half. And if we're asked to find probability that if we're asked to find f of 3, that is, we're asked to find the probability that x is less than or equal to 3, right? So that adds up to 1. Okay, we can easily see that from the table. Expected value, which is also referred to the mean or expectation or the average value. Okay, and we're talking about for a discrete probability distribution. So let's consider again that family of 3 children. How many would you expect to be girls? Now the formula for expected value or expectation or average value or mean, it's equal to x, the sum of x times the corresponding probabilities. That's what this formula is saying. And the expected value is denoted by E of x. Okay, so E of x is the sum of all the product of all the possible values of x times the corresponding probability. An example, of course, will clarify this for you. So let's again look at that table that looked at the family of 3 children, and the number of girls was our x random variable. We need to find the mean or the expected number of girls in a family. The formula says x times the corresponding probability. So the first x is 0, corresponding probability is 1 over 8. The next x is 1, corresponding probability is 3 over 8. So 0 times 1 over 8 gives me 0. 1 times 3 over 8 gives me 3 over 8. 2 times 3 over 8 gives me 6 over 8. 3 times 1 over 8 gives me 3 over 8. Now I'm going to sum that. It works out to be 12 over 8, which is 1.5. So I'll expect 1.5 of the children to be girls. Of course, we cannot have 0.5 of a girl, but statistically, that would be the value. Okay, there's an equal chance of you having a boy and equal chance of having a girl. Now that we have found the mean, of course, we need to find, the spread of this value. So we're looking on variance as our measure of spread. And the formula for variance, in this case, it's a sum of x minus the mean squared times the corresponding probability. So you're going to find out each value or each of those x values deviate from the mean. Then you're going to square it. Then you're going to multiply by the corresponding probability. So recall that the mean was 1.5. So our first x value is 0. 0 minus 1.5 is negative 1.5. We're going to now square that to give us 2.25. And then we're going to multiply the 2 1/4 by the probability 1 over 8. And that gives us 9 over 32. Similarly, x is 1. 1 minus 1 1/2 is negative 1/2. We're going to square that to get 1/4. Then we're going to multiply that by the probability of 3 over 8. We'll get 3 over 32. We're going to do that for x equal 2 and also x equal to 3. Then we're going to sum this last row, 9 over 32, 3 over 32, 3 over 32 plus 9 over 32 to give us a variance of 3 over 4. Now the standard deviation would be the square root of the variance. So the standard deviation would be the variance 3 over 4, square root of that, to give us 0.866, I believe that last number is. Okay, so now you know for a discrete probability distribution given to us in that probability distribution table, we know how to find the mean and the standard deviation. And we know that the sum of the probabilities must add up to 1. So now we're going to move on to looking at two special discrete probability distributions. The first one is the binomial distribution. Now, when the problems are given to you, it's not going to state that it's a binomial distribution problem. So you need to know what are the conditions that should be present to use binomial distribution. Now, for binomial distribution, there are 4 conditions that should be present. Now, let me just look on this scenario. This is a binomial distribution scenario. Let's consider tossing a coin 40 times and recording the number of heads obtained. Okay, this is binomial. Now, there are 4 conditions that will help me to make the conclusion that it's binomial. The first condition is that there must be a finite number of trials or observations, right? And here for this experiment, I'm tossing the coin 40 times. So that's a finite number of trials, okay, or observations. So n is equal to 40. The other condition is that each trial has only 2 possible outcomes, right? One outcome we're going to consider success and the other outcome we're going to consider failure. So when I toss this coin, I'm going to have either head or tail. 2 possible outcomes. Getting a head would be considered a success because I'm recording the number of heads, so that's success. So getting a tail would be considered a failure, or not getting a head would be considered a failure. The other condition is that the probability of success must be constant from trial to trial. Now remember, success is the probability of getting a head. Success is getting head. Now the probability of getting a head is 1 over 2, and that is constant each time you toss the coin. That doesn't change. So the probability of success is constant from trial to trial in this scenario that we're looking at. Number 4, the outcome of any trial is independent of the outcome of any other trial. And this is so for the scenario that we're looking at. If we toss the coin and we get a head, when we toss the coin again, because we got a head before, that has nothing to do with the next outcome, right? So the 4 conditions are present here for us to realize that this is a binomial situation. Now, if our random variable is binomially distributed, we normally denote it as x. We use this little symbol to indicate x is binomially distributed, BIN for short. And in brackets, we have the parameters of the binomial distribution. And the parameters for the binomial distribution, these are n and p. N is the finite number of trials, and p is the probability of success. So for the scenario before, n, the finite number of trials would be equal to 40, and p, the probability of success, would be equal to 1/2. So when we're doing the question and we are denoting it, we will input 40 and 1/2 for the values of n and p respectively. Now there's a special formula for working out probability distribution. To find the probability, it's equal to n, the number of trials, n combination x, the variable, the value of interest, p, which is the probability of success to the power of x, times q, which is the probability of failure to the power of n minus x. Now the probability of failure is going to be 1 minus the probability of success, because p and q must be equal to 1. So let's look on this example. Let's consider two women. They're having babies. What is the probability that both of these women will have boys? Now, it doesn't indicate that it's a binomial distribution question, but we can recognize the four conditions that are present. The first one is that there is a finite number of trials. N is equal to 2. We're looking at two women. Okay, so N is equal to 2. The other condition is that there must be two possible outcomes, one of which is considered success and the other failure. So in this case, success is having a boy, failure will be having a girl. Okay, in this case, all right? The probability of success must be constant from trial to trials. That's the other condition. And the probability of having a boy is a half, right? And if you have, for you to have an next child, the probability of having a boy is still a half. Okay, so that's constant. And the other one is that the outcomes are independent. So the first woman having a boy will not have anything to do with the second woman having a boy. Okay? So our solutions now. In order to solve this problem, we need to define firstly what our random variable is. And X is the number of boys. That's what we are interested in, the number of boys. Okay? Now the number of boys is binomially distributed. N is 2 and P is a half. Now note that the possible values of X is equal to 0, 1, and 2. That means both women, none of them could have boys. That means both had girls, or one had a boy, or both of them had boys. So those are the possible values of X. Now let's find the probability that X is equal to 2. That is, both of these women had boys. Now remember, N is 2, X is 2, P is a half, and Q is also a half. So we plug those values in the formula. 2 combination 2. And this is a function that you will find on your calculator. All right. So you press 2, then the combination button, then 2. Some calculators vary, so you should know how your calculator works. So that's N combination X, 2 combination 2, times a half to the power of 2, times a quarter to the power of, times a half rather, to the power of 0. Gives you an answer of a quarter. All right, then we're going to look on another example. Okay. The proportion of allergy patients who show a positive reaction to a certain skin test is 0.66. Let us assume that an average of 5 patients a day are tested at the allergy clinic. Calculate the probability that among any 5 patients, 3 will give a positive reaction. So we are interested in the number of patients with a positive reaction to this test. So notice in the solutions, I've defined X as the number of patients with a positive reaction. All right. Now, X has binomial distribution. We are looking at 5 patients, so N is 5. And the probability of having a positive reaction is 0.66. That's our P. Okay. You would have looked at the question and realized that binomial is suitable because the 4 conditions are present. So now we're going to plug these values in our formula. We need to find a probability that X is equal to 3. The number of patients with a positive reaction is equal to 3. This is equal to 5 combination 3. Punch it in the calculator, whatever that works out to be. You're going to multiply that value by 0.66 to the third power, which is our X. Whatever that works out to be, we're going to multiply it by 0.34, which is the probability of failure, to the second power. Okay, we would have gotten 0.34 by saying 1 minus 0.66. So our answer would be 0.33. Another example, same scenario. The proportion of patients that show a positive reaction to the certain skin disease is 0.66. We have 5 patients. Calculate the probability that among any 5 patients, all will give a positive reaction. Okay, so in this case, X is equal to 5. The number of patients with a positive reaction is equal to 5. Okay, so 5 is our N, combination 5 is our X, times 0.66 to the 5th power, times 0.34 to the 0. And punch that in the calculator to get your answer. Another example, same scenario, 0.66 of the patients have a positive reaction. We're looking at 5 patients. Calculate the probability that among any 5 patients, 2 will give a negative reaction. Now notice this is a negative reaction, and the question told us 0.66 has a positive reaction. So in this case, our random variable of interest is the number of patients with a negative reaction. So n is 5, but p this time is 0.34. Because that's the probability of the patient having a negative reaction to the skin test. Okay, we are interested in the probability 2 of the 5. So therefore, x is equal to 2. So in our formula, 5 combination 2, p would be 0.34. We're going to raise that to the power of 2. Probability of failure will be 0.66. We're going to raise that to the power of 3. Punch it in the calculator. Your answer should be 0.0332. Another example, calculate the probability that among any 5 patients, at least one will give a positive reaction. All right, at least one means we're looking for one or more. So that means you have to find the probability that x is equal to 1. One patient had a positive reaction, x is equal to 2. We have to also find x is equal to 3, plus x is equal to 4, plus x is equal to 5. Okay, that's a tedious task. We can work this out easier because you may recall, or you should recall, that the sum of all the possible probabilities must add up to 1. So the possible values of x here, x can be 0, x can be 1, x can be 2, x can be 3, x can be 4, x can be 5. Now when you add all the probabilities associated with those values of x, it must be equal to 1. So instead of working out the probability that x is equal to 1, 2, 3, 4, and 5, we can work out the probability that x is equal to 0 and then take that answer from 1 because the sum of all of those probabilities must be equal to 1. Okay, so we can work this problem out by saying 1 minus the probability that x is equal to 0. So we'll have to find the probability that x is equal to 0, 5 combination 0, 0.66 to the 0, 0.34 to the 5th power. And then we're going to take that value from 1. All right, just a note that any value raised to the power of 0 is 1. All right. Now, the mean and the variance of a binomial distribution. So if x is binomially distributed with parameters n and p, then the mean or the expected value or expectation is equal to n times p. Whatever the value of n is times p. And the variance is n times p times q. And if the variance is n times p times q, then that means the standard deviation is the square root of n times p times q. We're going to move on now to the other special probability distribution, discrete probability distribution, which is the Poisson distribution. Okay. Now the Poisson distribution, here you are interested in the number of occurrences of a certain event within a given interval. So we're recording the number of times a particular event occurs in a unit time or interval. Okay. Now x is going to be a random variable. Okay, so the outcome is random. The probability that an event occur in a particular unit time or interval is the same for all the other unit times or intervals. The number of events that occur in a unit is independent of the number of events that occurs in other units. As the unit time or interval gets smaller, the probability that 2 or more events will occur in that unit gets closer to 0. All right, and an example would be the probability of people contracting a very rare disease, or another example could be the number of accidents that are roundabout in a given month. Right, something like that will constitute a Poisson distribution. Okay, we're going to look on an example on how to denote these probability distributions. All right, so for Poisson, you have to remember the conditions would be that x is a discrete random variable. The occurrences of each value of the variable must be random. and the occurrences must be entirely independent of each other. If X has Poisson distribution, we denote it as X, as this little symbol, Poisson, P-O, we denote it. And this parameter is lambda, okay, lambda. And lambda is the average number of events in a given interval. The formula is e to the minus lambda, lambda to the x times x factorial. Now, e is a function you should find on your calculator. It's above ln. So usually you have to do shift or second function to get to that e. And factorials, x factorial, that factorial function should also be on your calculator. Now I'll just quickly talk about the mean and the variance of the Poisson, because the mean is lambda, the variance is also lambda, and the standard deviation is the square root of lambda. So that's very easy. Now let's look on an example. At clinic A, the number of incorrect test results for a particular disease averages 2.1 per day. What is the probability that 4 incorrect test results for the disease will occur in a given day? So realize we're looking on X is going to be discrete. The number of incorrect test results for the disease is that's discrete. Notice it's for a given interval. We're looking in a given day. And notice that our outcomes would be independent. So when we define our random variable here, we have to indicate the interval. So X is the number of incorrect test results for disease in a given day. All right? And X has Poisson distribution 2.1, or it averages 2.1 per day. The possible values of X could be 0, 1, 2, 3, all the way up to infinity. So Poisson doesn't have to be finite as binomial distribution was. So now all we need is lambda and the value of X that we are interested in. So the number, we are interested in the probability of 4 incorrect test results. So X is equal to 4. All right, so e to the power of lambda, lambda is negative 2.1, times lambda, 2.1, to the x, which is 4 over 4 factorial. And you punch that in your calculator, your answer should be 0.0992. Let's look on an example. Same scenario, but this time, what is the probability that at least 2 incorrect test results will occur on a given day? Right, so X is still the number of incorrect test results for disease on a given day. It's still binomially Poissonally distributed with 2.1. We want to find at least 2. At least 2 means 2 or more. So X is equal to 2, X is equal to 3, X could be equal to 4, X could be equal to 5, all the way to infinity. Now, to work this problem out, remember all the possible values of all the probabilities must add up to 1. So what we're going to do, instead of working out probability when X is 2, probability when X is 3, all the way up to infinity, we will work out the probability that X is equal to 0 and 1. And then take those two probabilities from 1. The sum of all the probabilities must be equal to 1. All right? So we'll find the probability that X is 0. Find the probability that X is equal to 1. Sum those values and take it from 1. Let's look on another example. Same scenario. However, what is the probability that 6 incorrect test results for the disease will occur in a 5-day period? Right? So we're not interested here in just 1 day, but in a 5-day period. So we are told that it averages 2.1 per day. So we need to work out what the average would be for 5 days. So that would be 2.1 times 5. So our lambda is now 10.5. And notice X, my definition for X has changed. X is now the number of incorrect test results for the disease in a 5-day period. Right? So you have to define your X whenever you're working out these problems, and you have to ensure that the lambda corresponds with the time interval, or whatever the interval is. It's not limited to time. All right, so X is equal to 6. You want to find the probability of 6 incorrect test results, so X is 6. lambda is 10.5. So it's e to the minus 10.5 negative e to the minus 10.5 times 10.5 to the 6 over 6 factorial. Punch it in your calculator and you'll have the answer. Now there are times when a situation is binomial and we can use Poisson to work the problem out. All right. So Poisson distribution will give you a good approximation to a binomial distribution when n is large and p is small. Usually large in this case when n is greater than 50. It's better, the approximation is closer when n is greater than 50 and when p is close to 0. The condition you would use is n times p is less than 5. So if n times p is less than 5 and n is large, 30 or more, then you can use the Poisson distribution to work out a binomial situation. So let's look on this example. Suppose we sample 100 items from a production line that is producing on average 2% defects. What's the probability of exactly 3 defective items in our sample? Now this is a binomial situation. N is finite. We're looking at 100 items. We're looking at defective items. So the item can be defective or not. So 2 possible outcomes. Probability of defective item is 2%, and they're independent, right? So we can work this out using binomial. N is 100, p is 0.02, x is equal to 3. Now notice my answer is 0.182. However, notice n is large and notice p is very small. So we're going to use this using Poisson. We're going to work this out using Poisson approximation to binomial. All right, so x is the number of defectives in a sample of 100, okay? And it's binomially distributed. N is 100, p is equal to 0.02. Now, since n is large and p is small, and also since n times p works out to be 2, which is less than 5, we are going to use the Poisson approximation. Now, to get lambda is going to be equal to n times p, which is 2. All right, so e to the minus 2, 2 to the third power over 3 factorial gave us 0.1804. And notice when we worked it out binomial, it was 0.182. So very close approximation. All right, now if you're going to use Poisson approximation to a binomial situation, you have to justify its use and say n is equal to, n is large, p is small, and n times p is less than 5. You have to justify it. All right, so that brings us to the end of the presentation. Thanks for listening. I hope you found it useful.